All right, so we got log base 2 of x minus 1. So this is all graphing. The instructions are graph, and then there's some extra ones. So let's start with log base 2 of x. And so we have y equals that. Now remember, that right there, the y is the power of 2. So all the powers of 2. That's what y is. That's why we have logs. Logs equal the exponents, right? So when you set up a little chart here, this is what I recommend on logs. This is one of the few times where I actually recommend making a little chart if you forget what it looks like. So 2 to the 0 is 1. 2 to the 0 is 1, so x is the 1, y is the 0. Because 2 to 0 is 1. That's a nice one. And then let's make nice ones. So 2 to the first is 2. So 2 to the first, that would be the y would be the 1, is 2. And then 4 is 2, 8 is 3, and we could go to 16 and 4, but I'd run out of room there. So that would be the chart, the XY chart for a log graph. So I could plot the point 1, 0. 2 would be 1. 3, 4 would be 2. 5, 6, 7, 8 would be 3. And so this is, that's log base 2 of x. But our rules say for transformations of graphs that if you have a minus 1 on the inside, that moves everything right 1. So now there is an asymptote here at y equals 0 for log base 2 of x. So the asymptote gets moved over 1, and then all these points get moved over 1. So here's the actual graph that I would need to see. And don't forget to draw in your asymptote. That would be worth a point. Parametric. It is nice to know that if you have 3 sine and 5 cosine, because 3 and 5 are different, that is an ellipse. Now, if those were exactly the same, it'd be if it was 5 sine and 5 cosine, that'd be a circle. So let's since this is trig and we're only graphing it from 0 to pi, we'll plug in the t values, and we need the x values, and we need the y values. So we'll go 0, pi over 2, and pi. When I plug 0 in for sine of 0 is 0, so that's 0. Cosine of 0 is 1, so that becomes 5. And then pi over 2, sine of pi over 2 is 0. 1. 3 times 1 is 3, 0. Then when we plug in pi to both of these, we get 0, negative 5. Now we can plug in only 3 points because hopefully you know that when you graph sine and cosine, they create these curves. They're not these jagged little lines, right? So we have 0, 5. Yeah, 0, 5. 1, 2, 3, 4, 5. We have 3, 0. 1, 2, 3, 0. Then we have 0, negative 5. 1, 2, 3, 4, 5 down here. It says show direction. Well, I haven't really graphed it yet. It's this nice curve is how this graphs. Show direction. Well, I started at the top and I worked my way to the bottom. So that's how you show direction. Just put a few arrows on it, on the curve. Find initial point. Initial point is where we started. So the initial point would be 0, 5. The terminal point is where we ended. We ended at 0, negative 5. And then we're going to give the Cartesian equivalent. Well, that's an ellipse. But we know that sine squared t plus cosine squared t is equal to 1. We know that from our unit circle. Now, so we can also say that x over 3 is equal to sine of t. And for the y, we divide by 5. Y divided by 5 is cosine of t. So sine squared plus cosine squared equals 1. Then x squared over 9 plus y squared over 25 must equal 1. And that's your equation of an ellipse. This is an equation for a hyperbola. The center of the hyperbola is 1, negative 3. So let's go over to 1, negative 3. And then since 25 is under the x, we'll go right and left 5 from the center. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So 5 right and left. From the center, because 25 is under the x, right and left. Y is up and down. So from the center, we'll go 3 up and down. And that's because of that 9, not because of that plus 3. So 3 up and down. 1, 2, 3 up. 1, 2, 3 down. And then there's a process to graph a hyperbola. And that's where you make the box. Now, you got to be careful on the test because ellipses start out the exact same way. So I've had lots of ellipses graphed for hyperbolas because they start out the exact same way. But for a hyperbola, you make the box. Then you draw the diagonals of the box or the rectangle. And these are just guidelines for the actual hyperbola. And then now since x is first, bigger matters on an ellipse, first matters on a hyperbola. Because x is first, this is a right and left hyperbola, a horizontal one. If y was first, then I'd be drawing this up and down. So this one goes right and left. And we were just asked to graph it. That's it right there. Here's the rational ones, and with rational ones we are asked to provide lots of information. So let's go through one. The first thing that you need to do when you're given a rational equation is factor the top and the bottom. So x plus 2, x minus 1. And we have x plus 3, x minus 1. Now those cancel, which creates a hole in the graph, which is a discontinuity in the types. So removable at x equals 1. And if you want to get real specific, it's the point 1 comma something, and to get the something, you plug 1 into what's left over. So 1 makes that factor 0. The actual point is you can't plug 1 into the other part of it. It makes 0 in the denominator. So you plug the 1 into what remains, and that'll be 3/4. So 1 3/4. Now the good news, well, there's a hole in the graph there, but the good news is that's going to kind of be a reference point for us. So at 1 3/4, there's a hole in the graph. And the curve will go through that hole. All right, so now we treat this as a brand new problem. Now we get all the rest of the information off of what's left over. So the first thing you need to check for, are there any holes? Does anything cancel out? X-intercepts. That's what makes the top 0. So x equals -2. So the point is -2, 0. -2, 0. There's your x-intercept. The y-intercept, you plug 0 in for the x's. So 0 plus 2 over 0 plus 3. And I'll write this out so when you look back at your notes, hopefully you can tell what I did. I could have just written 2/3 up there, but if you want to make a note for later how we got that, write what I write. 0 plus 2, 0 plus 3. So 2/3, so 0 2/3. So the point is 0 2/3. That's about right there, I would say. Let's not worry about domain. We got the discontinuity so far. Asymptotes is probably where we should go next. Asymptote, the vertical asymptote is what makes the denominator 0. So x equals -3. So 1, 2, 3. X equals -3 is a vertical asymptote. So we'll list that as an infinite discontinuity at x equals -3. So there's an infinite discontinuity, a vertical asymptote in other words. That kind of goes hand in hand. So we got horizontal asymptotes. The powers are exactly the same, x to the first over x to the first. So y equals 1 is a horizontal asymptote. That's not a discontinuity, though. That'll affect our end behavior. Use limits, behavior at vertical. All right, everything can be done now after we get the graph done. Well, I'm pretty confident I know what the right side of the vertical asymptote looks like. I'm very confident it looks like that on the right side. And I had a whole bunch of points on the right side of the vertical asymptote, but I have nothing on the left side. So we're going to have to do a little work here. 1, 2, 3, negative 4. So I'm going to evaluate the function at negative 4. And if I go back to when I canceled, it'd be negative 4 plus 2 over negative 4 plus 3. So negative 2 over negative 1 looks like positive 2. 1, 2, positive 2. So I'm pretty confident that it looks like that based on that 1 point. Now, if you're not sure, just plot some more points and play connect the dots with a smooth curve. Domain. Now we can go back and we can answer the other questions. The domain goes from negative infinity to negative 3, union with negative 3 to, where's that hole at? That hole's at 1, and then union with 1 to infinity. So there's the domain. You got to skip over the discontinuities, negative 3 and 1. I got both discontinuities. I got the infinite and the removable. I got the asymptotes, the end behavior. And I can say, because I have a horizontal asymptote, I can sum it up and say the limit as x approaches plus or minus infinity of the function is equal to 1. So there's the end behavior. Happens to be exactly the same on both sides, so I can sum it up in one statement. Use limits to describe behavior at vertical asymptotes. So the limit as x approaches negative 3 from the left is shooting up to positive infinity. And then the limit as x approaches negative 3 from the right of f of x is equal to negative infinity. And hopefully I've answered. If I haven't answered any of that, let me know. I think I got everything. X-intercepts, top 0. Y-intercepts, plug 0 in for x. Discontinuities, you can have holes and usually vertical asymptotes. Asymptotes, that's what makes the denominator 0. And then also you have your ending behavior for asymptotes, the horizontal ones. Then from that horizontal asymptote, you get your ending behavior, and then at any vertical, I could ask you, well, what's happening on either side? Sometimes they both go to infinity, sometimes they both go to negative infinity. Lots of things can happen. Any questions? Lots of information there. How about some trig functions? The first thing I like to do on this is to get the period. And the period is pi over k. So if that was sine of 2x, it's a little easier because then the period is pi over 2. K being the coefficient of x. So this one is 2 pi. 2 pi. It's been a while. So this would be pi. The normal period of sine is 2 pi. So we have 2 pi over 1/2, 4 pi. So the period for this is 4 pi. So to cheat and make all of these graphs look exactly the same, we just go 1, 2, 3, 4 spot is now worth 4 pi. 1, 2, 3, 4 spot, negative, I didn't write that real well. Let's try that again. Negative 4 pi. We have the period taken care of. Now we got to take care of the 4 and the 1. The 4 is the amplitude. So from sine starts at 0, and then I'd go up to 1, 2, 3, up to 4, down to 0, 1, 2, 3, 4, and back to 0. So then here I'd go 1, 2, 3, 4, back to 0, up to 4, back to 0. But now that plus 1 on the outside means now raise all of these up 1. So up 1, up 1, up 1, up 1. I missed this one right here. Here, there. And this one. Now it should create this nice, smooth wave. There we go. Tricky part's probably the period there. Well, the real tricky part is when you have horizontal phase shift. That's what really gets fun. Especially if you mark them as pi over 2s and all of a sudden it's moving over pi over 3. That's when it really gets interesting. All right, how about y equals cotangent? Think about your principal quadrants. Cotangent is, well, we don't want to split this over, undefined. So maybe cotangent wouldn't work that way. But if you have 1, 0, tangent sine over cosine, so this is cosine over sine. This is undefined. This is the point 0, 1. That's actually 0. And then when you have negative 1, 0, the cotangent of pi is back to undefined. And we don't like to graph one period of this split across the undefined. We split it across the 0. So we have 0, 0's here. We could have pi over 2 here and pi here. So tangent is split over the y-axis because then you'll be between from negative pi over 2 to pi over 2. You'll split it across the 0. Well, we'll split this across the 0, which means we have to shift over a little bit. Then pi over 4 is 1. So if we call this 1, pi over 4 is 1, and then 3 pi over 4 is negative 1. So we're down here. And we have vertical asymptotes right here. That's the undefined part. And then this shoots off to infinity as you go left. Then as you go right, we're going down to negative infinity. Now tangents split over that y-axis. It goes from negative pi over 2 to pi over 2. But cotangent is shifted off to the right. So that's one period of cotangent. Any questions? Then we get to my favorite. I love polar. 5 sine is a circle. You can, remember we double this and that's what we count by. But sine finishes in pi. So if you go theta r, you go 0, we're going to count by pi over 2's. Pi over 2's, remember you double the coefficient. 0 pi over 2 and then to pi. And you should be able to complete the graph with 3 points. But we know that when you graph these sine and cosine, they curve. They're curves. So sine of 0 is 0. Sine of pi over 2 is 1. 1 times 5 is 5. Then sine of pi is back to 0. So you have 0, 0. But then when you go to pi over 2, that's at 1, 2, 3, 4, 5. But what you need to know, you need to have a little bit of knowledge, is that this kind of circles around. That's a circle. That should be a perfect circle, right? Sine affects the y. That's why this circle is pushed up above the x-axis with a radius of 2.5. Has a diameter of 5. And then I just picked one of the others that we have. This happens to be a cardioid. We double the coefficient again. That's a nice rule to have every time. But we have to go all the way to 2 pi for this. So theta r, so 0, pi over 2 pi, 3 pi over 2, and then we should be able to finish it in 2 pi. Cosine of 0 is 1, so this is 6. Pi over 2 is 0, that makes that 3, because this part right here will be 0. Pi, cosine of pi is negative 1, so there's the 0. That's what makes it a cardioid. The r is 0. 3 pi over 2 is back, this whole piece is back to 0 again, so that's 3. And then when we get to 2 pi, we're back to 6. So we have 6, 3, 0, 3, 6. 1, 2, 3, 4, 5, 6. 3, 1, 2, 3 up here. 0, 1, 2, 3, then back to 6. Now we don't draw straight lines for these. We know that when we graph them, they are curved. These are curves. So we go a little bit wider than this one. Bounce off the pole, go a little wider than this one, then circle around. So it's kind of a fat heart.